Okay, we will start to continue from our last script, which was the script number 22. I think we have a problem at the end of the script that my computer at home was hang. Okay, I couldn't go on. So, but the material almost through the finish line already. So we're gonna start this clip, okay, by reviewing what we the end of the last clip is that we are talking about solving the Bowman model here, okay, which can be written as you saw on the screen here, or you're seeing in the screen here. Okay, we already explained this model, and then the original paper, okay, last clip, okay, we review, okay, the important results, okay, of the Bowman model that can be reformulated as a transportation problem, okay, where the source of capacity represents the source of supply, okay, and the sales in each period represent the demand location or the customer demand, okay, and we also wrote a formulation here when we add the uncertain demand condition and we're using the discrete sample, okay, number of sample as a discrete number, okay, we call the capital N, okay, and in this form we also represent the only the demand size, okay, where the supply side is a deterministic, okay, and also we can apply, okay, what we call the Bender decomposition, okay, we already explained last time, okay, in this iterative routine as shown on the screen, okay, and today we will show you the implementation, okay, from the classic Bowman problem, okay. We're gonna go on and show you the as a spreadsheet, okay, we call this a Bowman uncertainty spreadsheet, which I already install you here, and I'm gonna show you the matching between the classical Bowman model and with this uncertain demand pattern, okay. The demand pattern is can be randomly generated according to this one in the first row on the column O P Q R S T, okay. In this one we planning 6 period ahead, okay. Can be weekly, daily, or monthly, whatever you want to use in practice, okay. We also have a cost of under, okay. If you are under demand, okay, if you want to fulfill the demand of back order cost, okay, which is a lot more expensive than the inventory cost. This one, the cost per under is can be explained like this, okay, that okay, the cost per unit of under the demand requirement, okay, you need to purchase more or put it in the back order form for the next period. And cost of over is mean that you already over allocate, so you have to wait until the next period to fulfill the additional and future coming demand, okay. And here's the table that the regular table down here, okay. In this case we are working on the 6 period planning problem, okay, and each period, okay, there are 3 sources of capacity. The regular capacity, which based on the working hours, okay, regular working hour, the overtime working hour, okay, and the outsource, okay, in case that your regular and overtime all together can still not be able to fulfill the demand, okay. So this is the classical transportation table, okay, as you already saw from the paper of Bowman, okay. And for each source of capacity, okay, you also have, and this is a given capacity value here, okay, and certainly the up here is a cost per unit of under and over, okay, for each period, not all equal, okay. You can see that we already put some formula to evaluate the total cost. In this case, you decide to do nothing. Decide not to use any capacity at all. How come the result of total expected cost, where is this value coming from? I will explain you later. Let's look at the related cost coefficient corresponding location here and with all the variable here. In this case, we also allow you, the difference is that we also allow you to have to use the future period, to fulfill, the demand for the previous period. In this case, you might call this a back order. It's a back order cost. It means that suppose for some specific period where you have a lot of demand, that you cannot really use, even though you use all the capacity in that period, it's still not enough. So you can use you will see that from the paper of Bowman. I will take you back, to see the regular paper of Bowman. Here. You can see that we in this case we do not allow to have a back order cost. So except that you can produce to keep it to use in the future period. But if we have a cost element down here, to replace that straight line, here, it means that you allow to have a future, to use a future capacity to fulfill the past period. And in reality, sometimes can happen, sometimes, just portion, not all. Some of them have to be classified as a lost sale. So let's look at the here. Now you understand this is a cost. It means that this is a regular cost. For if you using the current capacity of both regular overtime and outsource in that period. But when you use that for the future period, the cost keep increasing, right? Because you need to add the holding cost. And the same as you use the future period to fulfill the demand of the previous period here. You also have an additional cost down here. Here, this part. So in this case, we already add the back order here. You might not confuse the cost element here with here, the cost of under here. In case that you under, it means that because the cost of unit under and over here related to what we call the demand pattern here. So this is the demand pattern. The uncertainty uniform distribution is what at least 250 and most 300. At most 299. In this case, you use integer value here. And 301, this one is at least 300, at most 349. And so on until the sixth period. So we use this demand pattern here, to generate all possible demand, sample of uncertain demand down here. You can see that the capacity here is deterministic. This one is S sub I, S1, S2, S3, S4, right? We go back to the formulation. When you use adapt this for this Bowman, the S sub I here. X sub I j is all allocation in the table. But this one, you have several types of demand, which means the summation for all row in each column J. Column J represent the period of allocation. I is all source of capacity available. In that period, you sum it all together because of the different uncertain demand type. Can be classified several scenario K. So there's some risk, right, that you not be able to fulfill. In some pattern, so you need to add this balance, the I plus and I minus. This is pretty similar to what we did in the previous model. So when we add it here, this is summation J for all J. This is summation J, Xij. All the Xij is here. Xi for I represent the capacity type, and J represent the period of planning. So Xij need to be allocated here, and this is the associate cost, okay, per unit, the variable cost per unit here, okay, and this is a summation of xij, okay, for all j, for all period, okay. You want to make sure the sum in each row, okay, do not exceed the current capacity here. So this is the value that the summation here less than or equal to here, okay, in the same location, okay. So that's the deterministic point. But the problem is the summation for in each column, the summation for all row in each column here, okay. You do not know because whether they're gonna satisfy exactly all possible demand type that represent here. So I use the formula here to generate all some possible case down here, okay. So this is the sample of the uncertain demand, okay. So it means this is k equal 1, 2, 3 for all of the scenario here. So this is that generate the scenario, okay, the requirement according to the uniform distribution as represent here, okay, both here in the row 1. So we apply to generate, okay, and we can look at that how many scenario that happen, okay. Actually there's a lot, it can be infinite number, okay. No, it's not infinite, sorry, because you normally the range is only 50, right? So there are 50 possible integer for each one, and there are 6 period, okay. So 50 times 50, okay, or 50 to the 6, okay. That's thought that can be a very large number, large positive number, okay. But we didn't generate for all possible, okay. We only generate around, I think, in this case 10,000 scenario, okay. For 10,000 scenario, okay, that we generate here, okay, the summation for all row in each column, okay, can be either under requirement here, okay. In this case, okay, it's all under requirement because now we didn't allocate any number for x by j, okay. X by j represent the number of production, okay, using capacity type I to fulfill the demand at period j, okay. So now you can see that all, because the current solution at the table is we didn't allocate anything, so it's always under requirement, okay. So there will be no over requirement here. So I already fixed the formula for you here, okay, to check whether, you know, it's going to be under or over, okay. You might try out by putting some number, okay, here, okay. Like for example, I'm going to produce here 150, okay, and then I'm going to do this another 50 here, okay, for period 2, okay, no, okay. I'm going to do overtime 40 and 10, something here. No, 40 and 10. Okay, I'm going to do outsource of 30 and 20. This is just an example that okay, once you already allocate here, okay, you can see there's some different down here already, okay. So the number of under requirements change, okay, and there'll be no over requirement because we haven't put on so many number before, okay. So but I want to make sure that this is a requirement for feasibility, that you want to make sure that the number that you put in each row, the summation do not exceed this number row by row, okay. But in here you can add some more, okay, like this one you can have 150, okay, and you might do it all here, 50 or even 100 here, okay. Or in this case you might use no, sorry, the 100 should be here, okay. In this one you might use 200, okay, and 25 here you can see, and 75, oh no, 75, no. it's getting slow here. Okay. Okay. You can see that when you put it all here, so there's some possibility now that you can have both. You see that the under, okay, requirement, the over requirement, okay. You can see that in this one I put so much number in period 2. So period 2 is over allocate. So you can see that in period 2 here. In period 1 you are under allocate, but for period 2 and period 3, okay, it become over allocate. Okay, it become over allocate. And then coming back to 4, 5, 6, we become under allocate again. Because I didn't put any number here for period 2 or 3. Certainly it caused the problem in period 2 because period 2, once you over allocate, it becomes the inventory that can also exceed the amount of demand for period 3. But when combining with the demand of period 4, okay, it becomes sufficient. Okay, so this is but we're gonna start with this 0 first. Okay, didn't respond well. Okay, and I'm gonna do this. Okay, because no, okay. Because the size of the table is very large due to this 10,000 row here of the demand pattern. So for each demand pattern, okay, once once you already once you're making a decision of allocate the production planning here, okay, it's gonna affect here that, okay, you can have for this initial of 0, okay, you always have just a under requirement, okay, because it's not enough, okay. You have plenty of capacity left, so all the demand cannot be fulfilled. So you need, it's always under requirement. There's no over requirement, and this is the balance equation, okay, balance equation to make sure that you, if you want to use the direct open solver to solve it, okay. But we're not gonna do it here. But we gonna illustrate you how to use the Bender decomposition here, okay. And then certainly we have cumulative or demand minus supply, okay. Why you want to find the cumulative minus demand minus supply? Because if you might remember that we have a special purpose algorithm. If you use the demand minus the supply side will be here, okay. In this case it's going to be the summation here, the summation of allocation down here. This is the demand side for each period, the summation for all number allocated for each column period, okay. Okay, here this is summation here, summation for all here, okay. So this is the demand side. So if you, for demand of each period, you minus this summation of demand. Let's go back to this one, the cut you see here, the coefficient of the cut here, okay. Here, the coefficient that multiply x by j is, you find the summation, okay, for all y, right, y star, y, this is the, you can find the y star with a pretty have the same optimum solution method using the old special purpose algorithm from the paper of Dr. Apisak here, because the dual formula is exactly the same form, except that the coefficient that multiply y sub jk is d sub jk, okay. Okay, it means demand of period j for scenario k minus summation I equal 1 to m x star ij. So we just check this, okay. But again, to find the optimum y here, since this is not the obvious solution, if you might remember from the paper, okay, from the paper of or maybe we go back and take a look at the PowerPoint, okay. Yeah, but it's not the same. Let's look at the paper of Apisak, okay. Okay, in order to solve, okay, for the special purpose problem here, okay, in this paper, as you might remember, we use S instead of k as compared to the slide. Okay, to solve this, okay, you just and to get y optimum to generate the optimality cut, okay, you need to find here, okay, the cumulative, okay, the cumulative of djs minus x star j, okay, the allocation that you use here, okay. This is but you know that this become x star j because it's a different problem. This is to solve this problem. So you have only x star j, x star j, because for each row only xj. But when you apply this to Bowman uncertainty, okay, your xj become let's look at the original. You have your x, instead of xj you become summation I equal 1. Instead of you have x1 x2 and so on, you have summation I equal 1 to n of x by j. So that's why the coefficient down here is changing to d sub jk minus summation here, okay. And this is what we did with this column of cumulative demand minus supply, okay. So the demand minus supply here, okay, is a cumulative value of the demand, okay, for each period, for each scenario, minus summation, okay. And in now all the summation is 0, because if you know the summation of xij for all y, we have no allocation of x of j, x by j here, okay. We have no allocation here as a starting point, okay. We have no allocation down here, okay. So all the cumulative here, okay, will be positive value for initially, and then we using this to allocate what we call the dual variable here. This is the optimum dual variable using the special purpose algorithm by checking the coefficient of the cumulative of demand minus supply. This is pretty similar to what we did before according to the paper of Apisak, but just being applied to fit with the model, the Bowman model, which is a transportation problem. Okay, so now you have period 1 to period 6, okay, and certainly once you already allocate the y value here, okay, you can find the corresponding dual variable here. So this is the optimum dual solution here, okay, based on you using a special purpose algorithm. So this one using the coefficients, okay, and this one using the coefficients to identify the u, this one u sub I k, and except the last period will be y, okay, and then we change u and y for each scenario to the optimum y value, okay. This one is the optimum y value, okay. Once you use this first, okay, this is the same solution, okay. Period 6 here and there the same because it's the same, it's already the dual solution, but this one you need to kind of substitute back, okay, but because from period 1 to period 5 it become u, okay, not y, except this y, okay. You still cannot remember what I'm talking about is that you have to go back to the classical paper, not the classic, I can't refer that, but my own work with Dr. Pisak here, okay, that okay, you want to solve for y, but in the special purpose algorithm, when you know the coefficients here of the cumulative value, you're gonna find u first by looking the sign of these coefficients, okay, to either pick either g or minus h, okay. But in this case you don't pick any minus value because you all have an under value for initially. So this one is a special purpose that y, this one is u1 to u5, okay, for scenario 1, okay. And then this the adjacent table here, just find the optimum y, okay. Once you know the optimum y, okay, you go back and take a look at the model of our Bender code here, okay. The coefficients to find the new x is summation k equal 1 to n of y star jk. It means that you're gonna sum up for each period j in scenario k. You summation for all scenario from scenario 1. In this case we have 10,000 scenarios. So you summation for all y, and then once you get that summation, you just use that as a core value and a minus the value of c sub by j. That will be the Bender cut coefficient according to x sub by j. And the right hand side can be summation j and k, d sub j k, y star sub j k. Okay, and then you to solve for the new x, okay, you need to add this summation xij less than or equal to s sub I also. Okay, so this is what we did here. Okay, now you get the optimum solution y here. Okay, you're going back to generate this what we call the Bender cut. Okay, to generate the Bender cut here. Okay, this is what you did. Okay, you have all this, you go down to the last alternative, you find the summation here. So this one is a summation y j k. Okay, summation for all k. This one sum for each for all row represent to count the number of scenario. Okay, this one is each column j equal 1 to 6. Okay, so this is a summation here. So the coefficient here, okay, when you want to find the Bender cut according to x sub by j, what you are doing here to use that value, okay, and put it in here. Here, this is the cut coefficient that automatic. You can see that the BD here is the last row for the period 1, the summation, and then you minus R5. R5 is what is here for each c sub I j here. Okay, so the next one, okay, we become the next column. This is for summation of y for period 2 for all scenario k, and then you minus here. Okay, and keep on going. Okay, and when you go to the second row, it become again summation y the same for all. For the same column, we use the summation y 1. Okay, for all k. Okay, y1 k for all k. Okay, and then you keep minus for each row. Okay, the cost relative for each row. So this become the Bender cut for the c sub I j. No, for x sub I j here to find, and this is the initial solution here. And also they already evaluate the cost here. So what is the cost here? Okay, it will be the summation for all allocation of x sub I j, and the cost per unit here of x sub I j. Okay, relative cost coefficient. And then you have what here? Okay, you have here the under value, okay, of under requirement here. This is I minus, over is I plus. Okay, you just combine all of this and with the cost coefficients. Okay, so what is our cost coefficient is up here. Okay, the cost of under and over. Okay, so what we did here, okay, so to make it more simpler in here, okay, look at the formula. The sum product, the first term of sum product is between these two for the cost per unit when you're using capacity source I on period j. Okay, the second one is a summation here, sum product of G1 and L1 here. This is the cost of under per unit of under, and then you multiply it from you O1. This one you go down, look down for the last one. Okay, I'm trying to combine. This one is a summation for all u. Okay, for 10,000 scenario. Okay, this is the summation of all under. Okay, for each period, all together for 10,000 scenario. And this one is there's none for the over because you didn't allocate any xij initially. So once you find this, you just use this summation. Okay, go back to the formula up here. Okay, you just use the summation in the line 10,025. Okay, and in column O and column W, start at column O to column T, and this one W to AB. Okay, and this one use a sum product of that summation with cost of under here G1, and this one is G2 to L2, which is the cost of O. And then this sum, okay, you have abbreviation down here to find it all, and then you need to divide with the number of scenario. V10024 is the number of scenario, which is in this case you can take a look at here V. okay, v1 over this is a 10,000. Okay, actually you can use this value wherever represent the countdown of the number of possible scenario. Okay, so this one is also assumed to have a uniform distribution. So this one is the expected cost. It means that if you don't do anything, you're not going to produce anything. Okay, you're going to go and use the back order, use the outsource additional capacity that not belong to the capacity under control here. Okay, so you're going to end up finishing 72,656, okay, 0.7506 unit of total cost, okay, according to here. Okay, and this is the bender. This is just one, okay, you remember that this is just one bender constraint, because now you have x sub by j, not just x sub j. And this is the right hand side, okay, and this is the t value. T have to be greater than or equal to the sum product here, okay, or no, not the bender coefficients here, okay, and have with the new value here, the new solution, which is here x sub by j. And certainly the summation here, okay, cannot be exceeded. The summation j for all j cannot exceed the capacity here, okay. And the t, okay, once you minus, okay, this cut coefficients, okay, sum product of this cut coefficient with the new x value that you want to find here, okay, need to be greater than or equal to this value, 72,656.74, which is where is this number come from? It's a sum product of, you can see that they represent the same number here, okay, the primal and dual is equal here, okay, expected cost here. So this one is the right hand side here, which is the, you might say that is the down here, okay, the y, the optimum y is here, okay, the optimum corresponding dual solution, okay. You need to find the sum product of all of this, okay, for 10,000 rows with the possible demand pattern here, the very first one. This is the uncertain demand. This is the DTS, okay, and this one is optimum y star, okay, y star TS, okay. And we're gonna find a place to keep the best solution now. So this is the initial solution is right here, the new solution here, okay. So you can see that this problem is a little bit more complicated because it's become the allocation in 2 dimensions, not just 1 dimension, just like the previous example, because your decision variable now is x sub by j, okay. And you go back here, okay. I'm gonna do the optimality cut constraint like this, okay. The right hand side, I'm gonna link this, okay, to C3, this one, okay. So this is the sum product of the DTS, the demand at period t scenario s for all of them, TS, and do the sum product of dot vector with the demand with the optimum dual variable y for all TS also, okay. So this is the right hand side, okay, and I'm gonna link it here to become the right hand side for this optimality cut constraint, and the left hand side is here, okay. I'm gonna do AA1, okay, AA1, and then plus the sum product here, sum product of what? Of this cutting, this is the cut constraint, okay, optimality cut constraint coefficient, okay. Have to multiply with the new x solution here, okay. So that's how we setting up the optimality cut, okay, to and then you can link it here, okay. This one, the constraint here, t is the objective function, plus this is a sum product between optimality cut constraint, okay, with the x sub by j greater than or equal to sum product of djk and y star jk, okay. That's this in the and additional constraint is here, summation xij less than or equal to si for all y. So we implement that algebra formula, okay, to this example. And so in the sub problem here, you need to find a new t value here, okay, the new t value, such as, okay, the left hand side is greater than the right hand side, and here, okay, left hand great. And also you want to make sure that your summation of x ij for all period, okay, for each capacity type I, okay, for each period, and you want to find the summation allocation, okay, of allocation for all column altogether here, okay, cannot exceed the current capacity that you have here. And that's all set up, okay, so we can, okay, start using an Excel solver to solve it, okay. So we're gonna start with this, okay, your objective function down here, okay, you want to minimize t here, and you want to minimize it, okay, this is the t value, is in the first row of column A. Your decision variable is t, okay, and then you have additional decision variable here is the new x here, xij for all here, okay, you want to make all here. So what is the constraint, okay, the constraint of x is that the summation here, okay, for each row, okay, your summation for all column, okay, cannot exceed what? Cannot exceed the capacity that you have here, row by row, okay, cannot exceed capacity here. And then what is your additional constraint? This is the bender cut constraint, this one, the right hand side here, we already must be greater than or equal to the left hand side greater than or equal to the right hand side, okay. And there's no fixed charge in this example. I'm not sure they're not working right, okay. Sometimes it happens. I think we need to rewrite it again, okay. Okay, okay, I'm gonna start with, okay, we're gonna add, okay, the first one, okay, we might start here, the left hand side here must be greater than or equal to the right hand side, okay, we add it up. And then the second constraint type is here, that the summation here, okay, less than or equal to, okay, here, the capacity here, and then we can type okay. Okay, so you have a constraint here, and we're using the simplex LP, okay, and we're ready to run. We solve it, okay. They're trying to find a new solution for you. Take some time because it involves to a large amount of number. Once you already found the optimum solution, you click it OK. Okay, you're gonna take a look at what is the new solution found. It's here. This is the solution that they found it for. They find it for you. It's a little different. Sometimes you don't really know what is going on, but they found this solution for you. But let's look at the t. The t didn't improve anything. But don't worry. It's gonna keep improving anyway. But then, what you need to do is that you want this new solution to generate your new cut here. The new cut down here. Okay? This is what you want to do. Okay? You want this, okay? Your new solution here to generate the new cut here. Okay? So, but before you're gonna replace this new solution here, okay, to this solution, okay? We still don't know what is the objective function. This is your old objective function is here, 72,656, and now you can see that the bender cut constant become feasible already. Remember before running, your left hand side is 0, okay? But you have to make sure that this is the cut number 1 here is for the sum product of the bender cut of this cut coefficient here, okay, with this cell, okay. And you have to know that when you replace this new solution to this location here, which is you initially you didn't allocate anything, but now you allocate the value here. All of this will be changed automatically, the new cut coefficient, because once you get the new solution, what's going to change in the system? You're going to have the difference of this one, the under requirement and over requirement results will be changed. But remember that this one is still based on the solution of xij is equal to 0 for all ij. But now you find the new feasible solution that you're going to generate the new cut. So to make sure that you have and you still don't know whether this solution is better than the previous solution until you put this solution to replace the old solution. But be careful that you don't replace it immediately, because once you replace it, your old cut coefficient here will be gone, because it's linked to the formula here. All this a formula. So to make sure that, but it's not quite as convenient as one dimension example that we do, because your xij now is up in both row and column here. So I'm going to reserve a space here that I put it here. So this is the previous cut coefficients, okay, down here. And to replace this one with the new solution found here, you need to, okay, put the old cut here. Okay, first make a copy, okay, of this is a old cut value, but you're gonna place it here, okay, just use the value. So this is the old cut, including the right hand side. So your right hand side here, okay, this is certainly gonna change. You're gonna copy it and just put it in here, okay, just the value. So this is become the previous cut, and you know that this previous cut, okay, cut coefficient number 1 down here, okay, will represent this cut constraint. But certainly this cut constraint will change or later. So you want to put it in here first, okay. So the left hand side here will become the sum product. Okay, you cannot copy the formula just like the old example, because now the location totally changed. Okay, you want to make sure that, okay, for the new solution x here, okay, you want to find the sum product with what? This one. Okay, this is the cut coefficients. Okay, so this is the left hand side, and then you need to plus what? Remember, plus t. This is the t value. Okay, this is a decision variable here that becomes the left hand side, which is exactly the same as the above. And the right hand side, okay, you can always say that, okay, I'm going to link this with the right hand side down here. Okay, so that's already finished the copy of this. Why you have to do that? Remember that this will be changed once you replace this with the new solution. Okay, now you're cutting, you have two solutions, so you have two optimality cut constraints here. So now you are ready to replace, okay, the old solution with this new solution. Okay, so I just make a copy of this current solution here for the bender cut, okay, and put it in here, okay, because when I put it in here, you get new upper bound to check, okay. So I'm going to replace this with just the value. Okay, so I put all of this. Okay, just take a while. Okay, now I put the solution. You see the tremendous improvement of the solution here. Now from 70,000, now the total expected cost reduced it to what? 27,000 here. So this is a better solution than the previous one. Therefore, you need to copy this. Okay, so this is a better solution than the previous one. You know that where we put the best solution, if you might remember. Okay, our best solution is put it in here. Okay, this is the best solution. You saw that. Okay, so now this is the you want to put the best solution that you found here, and the best objective function not here anymore, so it becomes this. This is your best solution. So in this case, we're not going to keep all the solution, okay? We just keep just the best solution. If you the next solution is better than this, you're going to replace it right here, okay? Here. You might remember the best solution here. Now your best solution become here, 20. So this is the best solution, the current best solution found in the very first iteration here. Okay, 27,036, okay, 0.30078, okay. And then once you know that, okay, the new solution is replacing here. Oh, sorry. Okay. And now your cutting plane, okay, the new optimality cut generated here, which certainly gonna be invisible because you want to solve for the new x to make this visible, and you expect that the t value will be increasing. Okay. So now your right hand side is here, okay, with this, and now you have a new cut coefficient down here. Okay, this is your new cut coefficient, and also you have the new optimality cut inequality. This is the old one. So now you're ready to find the new x here. Okay, certainly it's all automatically updated. That now you are having here with the special purpose algorithm. Okay, you end up having the new corresponding dual solution, optimum dual solution, right here on this table. Okay, why it look like this? Because now there are some path that you only have a under requirement only period 5, period 4, but the first 4 period become the over requirement based on this allocation. Okay, and that you get a better solution here. So now your upper bound is here, but your lower bound is still 0. Really still have a high duality gap. So I'm gonna solve, okay, for the new solution. Which what you have to change is that now you have to delete the old optimality cut, and then you add the new one. Okay, now your optimality cut down here. Okay, you have two constraints. These two have to be greater than or equal to these two, row by row. Okay, and you already saw it's invisible. The current solution is still invisible. So you want to find new solution, you just solve it. Okay, gonna take some time. Okay, you might observe that the solution become integer automatically. You didn't, when you solve it in just a LP mode. Okay, so you get the new solution. Let's look at the solution above here now. So now you get the new t, which is pretty good, right? From 0 now it's become 18,000, but you can see that the upper limit is 27,000. The duality gap in decreasing. Okay, and now you get the new solution here. Okay, this is the current solution, but the new solution was found here. So you get the new solution here. This is the new solution. Okay. In order to place the new solution, what you do? You remember that? So I reserve a new space for you, right? This is the previous cut. Okay. Cut coefficient. You have to make sure that you remove here. Okay. All the cut constraint here. Okay. From the current solution. Okay. You want to make a copy. Okay. And you put it in here. Okay, you're gonna put just the value here. This is the cut coefficients of the current cut, optimality cut. This is from the first iteration. So this one will be from the second iteration. And the right hand side, okay, the right hand side is right here. Okay, so just make a copy. Just try to memorize it. Okay, so the copy is here. Okay, so this is, so once you keep this cut coefficient constraint, okay, so you're now ready, right? Okay, because you're now ready to replace this solution to this solution. Okay, to identify the new cut again. Okay, this one take a little time because you cannot copy the formula because of the allocation of x in 2 dimensions altogether. Okay, so but you have to make sure that you move this to this. Okay, but I'm not gonna move cut 2 anymore. Okay, cut 2 already, cut number 2 already have the right formula. with this new solution with this cut 1. But you want to move cut 1 to cut 3 instead of. In this one you want to find the sum product, okay, of what? Okay, you're going back here, okay, you get, this is for the solution, the new solution that you're going to find, and then you want to do it with what? This one, you want to do it with the cut coefficient here, okay, and then, okay, you need to plus which value? Another value is the t, the AA here, okay, and then you get what? You get the same lower limit here. And then the right hand side, okay, the right hand side you just link it with the solution that you put it in here, which is here, okay. This is from the. So now you already finished, okay. Move this cutting plane optimality cut to here, okay. And then now you're ready. Now you have 3 constraints, okay, for optimality cut. So what you want to do with this is like this, okay. And also you take a look at the solution now. So now this becomes your best solution, right? Because you get to 76, 36, but you still don't know. This might give you a better solution here. But now you're ready, okay, to move this solution here. Okay, I'm gonna copy this solution, still not all integer. Okay, I'm gonna put it in here to replace this. Okay, just the value. So this is a new solution. Okay, take a while to recompute or get the better solution. Remember that the previous solution we keep it here is 270, 27. Okay, now you get the better solution here. Now you get, so this one is better than the previous. So now you just copy this. So right now this is the best solution. So you put that best solution right here. Okay, now this is your best solution. Now the best, and the best objective function now from 27,000 something. Okay, it become this value. Okay, you just copy it, and then what you are doing here, you just paste it here, just the value. So this right now, this is the current best solution, okay, and certainly with this new solution here, okay, with this new solution here, okay, it's generate the new cut here, okay, the left hand side, and will be infeasible. Instead, this already feasible, but this one infeasible. You're gonna solve it again for the next x here, okay. Once you get the next x here, you expect that this value will be increased, because you add more constraint, okay, from the previous problem. The t cannot getting smaller than this, it's going to get bigger because you add more constraint, okay. And you expect that the new t value will be closer to this value, the current best solution here, okay. We find out here, okay. At first we're gonna go back and call the solver routine here again, and then we just delete the previous optimality cut and add the new one. The new one will consist of what? The 3 optimality cut constraint, greater than or equal to this 3 value. Okay, I'm going to put OK here. Okay, once you know this, okay, we're going to turn to here. Okay, this is the current, oh no, you have to look at the t value here, the t value here. You expect that once you solve this problem, the t is getting larger. Okay, we're going to solve it here. Okay, so we start solving it. It takes some time. Okay, luckily this is the computer in my office, which is much faster than what I normally. Okay, we get the new solution here. So now the t increases to 19,000. The duality gap decreasing. Okay, approaching to verify your optimality. So this is your best solution now. No, not the best solution, the new solution that can generate the new cut. Okay, but you still don't know whether this solution is better than the previous one unless you make a copy of this new solution to this space to evaluate the total expected cost. Okay, but it becomes the iterative routine now. Okay, for the next iteration, you need to make a copy of that new cut coefficient here. Okay, and then you can put it in here, the previous constraint here. okay, you need to put it in here. And also you need to add, okay, cut number 4 here. Okay, you need to add cut number 4 here. Okay, move this cut to here, and then waiting for before you move the new solution here, okay, to generate the new cut. Okay, and after that you check whether the solution is better than the previous one. If it's better, you replace it with the current best solution. Unless if not, okay, you go on solving for the new t. Hopefully within a few iterations left, the t value and the total expected cost here, which is the c value here, are getting close and satisfy the strong duality theorem. Okay, but this is just a demonstration for you, but I'm gonna stop here. Okay, so this is just an Excel implementation as an example for you. Okay, but certainly you can find this in the file called Bowman uncertainty. Okay, what I thought here, and it's gonna start the file start to where I show you with the all zero element allocation in the very first iteration. So you can watch this clip again and again and repeat on this file, starting the behavior here. Okay, for this case of Bowman, I didn't do any Blender code for MATLAB. Okay, I just have a demonstration on the Excel file, which you can continue if you get used to, or you want to use it using what we call the Visual Basic, okay, macro Visual Basic to implement under the platform of Excel, okay, VBA Excel platform, okay. But for the MATLAB platform, okay, I think that from the lecture 1 to lecture 2, I already give you so many programs and code of MATLAB to solve the previous problem. Okay, so this is a big assignment for you. You might try to do it as a group if you the friend to help each other. That okay, this one I want you to use the previous knowledge and previous example that you learned. Okay, try to adapt the old program. Okay, okay. In this case, we only consider the variable cost, so there's no fixed charge. So you can use the lin plot as a subroutine. Okay, just like what we did in the Excel. Okay, to find a better solution until it reached the optimality condition. Okay, so for the Bowman case, okay, it become a huge project, the class project. Okay, for you to modify the code that I have been given you and MATLAB code, okay, to solve this problem. Okay, you might use the example on the Excel as a benchmark to develop your code. Okay, and also I think that when we go back to the original model here, okay, you can, I think, modify a lot that, because this one we only consider the uncertainty for the demand. Suppose you have uncertainty on both S sub I and D sub j. There is some uncertainty for capacity also. Okay, suppose these two have the simultaneous uncertainty. How can you adapt and modify your current code that you develop for just the uncertain demand? Suppose you have uncertain capacity also. Okay, and also from the last clip I did talk about there's some uncertainty for the coefficient here that multiply x sub I j on the left hand side. The coefficient of 1 or 1 multiplied to x sub I j here when they fit with the summation for the left hand side here. Okay, and but you don't really know. It means that if it's 1 times x sub I j, it means that in period j you can assign capacity type I to fulfill demand of period j, but also it can be uncertain, right? As I think that I did mention this a little bit from the last clip, that and we didn't consider much. This is the uncertainty that found when you try to matching the capacity to the demand for each period or the sales requirement for each period. Okay, and that will make a problem. All three together, uncertain part of the right hand side and the constraint coefficient can be simultaneously uncertain. That would make all combination going so much that you cannot just enumerate them all. Okay, so there are many room to work on this Bowman model. Okay, it even can continue to be some research work. Okay, if you are interested to go any further. Okay, but at this moment, okay, I think I have fulfilled all my expectation to introduce you, okay, in the last clip and this clip, to introduce you the famous paper of Bowman, okay, which is the deterministic case, okay, in here, and you can formulate the production scheduling as a transportation problem, okay, and then we apply the Bowman model when you consider only uncertain demand, okay, just uncertain demand, not uncertain capacity, okay, and also we develop apply what we call the Bender application, okay, and found the link of using the previous knowledge, okay, from the paper of this is just to from the paper of Apisak here, okay, that you can apply. Remember that this is the based on the Wagner and Witten, okay, concept, not the transportation model of Bowman, but the transition of inventory part from the consecutive adjacent period is exactly the same. They're leading to the same sub problem of dual problem that you can apply the special purpose algorithm to accelerate. You don't need to solve this problem 13, 14, 15 directly by using linear programming, and you can reformulate this to become a trivial solution that can speed up the computation time, as we found previously when you solve this problem. But I just show you that we can apply the same here to this problem, okay, and then come out with the scheme of Bender decomposition. And we also implement this idea on this file of Bowman uncertainty for you, and illustrate a couple of iterations starting from the start, okay, from the first optimality cut from the first solution, and we did it 2 iterations for you, illustrate to you here, okay. So that's about in terms of content of lecture 2, okay, on folder of lecture 2 on my online learning here, okay, that's can wraps up this one, the first 2 lecture here. But in the next clip, okay, sorry, we already done a lot of lecture, okay, but so far in some clip I did recommend you to continue your further study, doing some kind of homework or take-home exam as a take-home exam that you can practice yourself to understand the Excel file and also the MATLAB file attached, okay, in both folders, okay. But next time we're gonna wrap up and try to summarize you to see that so far in lecture 1 and 2, okay, what kind of problem in both Excel platform and MATLAB platform that you can do it as a homework or take home and accumulate all this work to submit it toward the end of the semester, okay. So at this moment you can go back and review all material here for lecture 1 and 2, okay. It's all done in terms of content, okay, and next time we'll see that what kind of homework problem or even the take-home exam you can do it, okay. See you then.